this example, let's explain it. So I will be doing 3 types of examples, okay? 3 different types. So this is the type 1, right? So the type 1 is when one loading region is applied on the beam, right? If you can remember from the exam or even before, when we formulating the bending moment diagram, we considered that whether the structure has 1 loading region, 2 loading region, or 3 or 4 or more. So this case is basically when 1 loading region is applied on the beam, and how do we go about determining the deflected shape of the beam. Okay, so the question is, the simply supported beam is subjected to a uniformly distributed load as shown below, and the question is asking us to use the flexural rigidity as EI. So in the exam or in the homework, probably you will see that E can be some value, or I can be some value, or I can be given in terms of the geometry of the cross section of this beam, right? So you should be able to find out what I is and what E is, right? I is, if you remember from statics, it's 1/12 BD to the power 3, right? B is the length that is going along the strong axis. D is the depth of the beam, or which is going perpendicular to the axis, if you remember that, okay? But in this case, for the simplicity, I'm using EI as it is, so we will use flexural rigidity as EI. All right, so the question is, determine the end rotation of the beam at A, okay, and the maximum deflection and the location where this maximum deflection is. All right, so let's consider the free body diagram for this beam. So I have used these reactions, okay? So we have this uniformly distributed load of 4 kilonewtons per meter, and then the reactions will be 20 kilonewtons each, all right, across this 10-meter span. And now what we will be doing is we need to formulate the bending moment equation, because the deflection is occurred due to the bending, correct? So therefore, we need to formulate the bending moment equation based on the applied load, right? So since we have the uniformly distributed load applied all across AB, we need to worry about only 1 loading region, right? So we will cut at a section which is X section, okay? And then we will consider the equilibrium for the moment, because we are interested in the moment, not shear at this point, okay? So when we formulate this, right, the counterclockwise moment is positive for the left-hand cut, M, and then the loading on top of it will be X times the loading intensity, which is 4. So 4X will be the total load, okay, 4X. That is exerted in the middle of this span, which is X over 2 from the moment, okay, the point that we take the moment. Therefore, the moment is 4X times X over 2. That is a positive or counterclockwise moment. And then because of this reaction, we have another moment, which is 20 times X, that is a negative moment, or clockwise moment, that is equals to 0. So the bending moment variation across the span AB can be given as M equals to negative X 2X squared plus 20X, okay? And if we remind ourselves the beam rotation and beam deflection, okay? So mx is something like this. So m is a function of x, or m is a function of the location that we are looking at along the beam. Therefore, this is called my mx, right? So I will, it gives me the permission to use this mx into this mx over here, and then carry out our calculation. So from this first equation, this is dy over dx, which is, again, I'm saying the slope at a point. Dy over dx equals to mx over ei. So mx is equals to this value, okay, that is right over here, is equals to ei. So since we have a constant ei throughout the member AB, we will have ei over here, okay. And now we will proceed. So, right, so dy over dx, again the slope, is equal to the integral of the moment over ei. So we will perform the integration here. So dy over dx comes over here, and then I'm putting this ei over here, okay, because it's same for the rest of the terms. And here, this is 2x to the power 3 over 3 plus 20x to the power 2 over 2 plus we have an integration constant, because now this is an indefinite integration, okay? So we need to find out this C1. Anyway, let's go further. So I'm going to integrate again, because now we are interested in now the second time integration, okay? So I'm doing the integration dy over dx equals to integration 1 over ei, same thing over here, okay? I do the integration. So the integration of dy over dx with respect to x will give me y, okay? Again, 1 over ei is constant, so I put it in outside of the brackets, and then I perform the integration for these three terms. So by seeing these two equations, the equation for the rotation over here and the equation for the deflection over here, we can see that we have two unknowns, C1 and C2. So now we have two unknown constants. So this is the place where we use the help of the boundary conditions and the continuity conditions, right? So if we look at the structure, right? So this is the structure, okay? We have a boundary conditions at A and B. So when we look at x equals to 0, this is where we start our measuring the length. When x is equals to 0, deflection is 0, because it is restraining the motion against the y direction or the vertical direction. Therefore, point A is not deflecting. Therefore, the y value is equals to 0. Similarly, when x is equal to 10, which is on the other side of the beam, we have a roller support. Again, we are restraining the motion against the y direction or the vertical direction. Therefore, we do not expect any deflection of the beam at B or at x equals to 10. Therefore, at x equals to 10, y is 0. So these two boundary conditions will allow us to determine these two constants, C1 and C2. Let's see how we can do that. So when x equals to 0, right, y is equal to 0. That is coming from our boundary condition. So let's plug in the values for x equals to 0 over here and y equals to 0. So when you see that, when you apply or substitute 0 for x terms here, you will see that these three terms will be disappeared, and we have a 0 here. Therefore, C2 equals to 0. Okay, that means C2, the integration constant, is 0, or C2 is 0. Again, I have another boundary condition that I can apply to find out the other unknown. When x equals to 10, y is equal to 0. So now let's substitute 10 into x, right? Over here, x equals to 10, x equals to 10, x equals to 10, And from the beginning, I know that C2 is equals to 0. So I can use C2 equals to 0. Okay. Now we will simplify this so that we will be able to get C1 equals to negative 500 over 3. So the question was asking, what is the rotation or the end rotation at A of the beam, right? So this is the equation that we have obtained for the rotation. Remember, this dy over dx is the rotation. So dy over dx at A when x equals to 0, right? So therefore, if I substitute x equals to 0, then I will be able to get the rotation or the slope at A. Because when x equals to 0, that is where I am on top of this support A. So I apply x equals to 0, x equals to 0. C1, we found that it is negative 500 over 3, okay? And therefore, dy over dx at A equals to negative 500 over 3. We have an EI outside of the bracket, and that will be multiplied by 3. So this will be the rotation or the slope at A. All right, now let's look at the other one. Where does the maximum deflection occur? Technically, by looking at the system or the loading system, we get to know that it should be in the middle, right? Because the loading is symmetric, the geometry is symmetric, so the maximum deflection should occur at the midspan. So how do we actually analytically say that it should be at the middle? It's pretty easy when we have the deflection curve. So this is my deflection curve, which I obtained by assigning the boundary conditions. Okay, same equation. So y equals to the same equation. And then if we need to find out where the maximum is occurring, right, what we need to do is we take this the derivative or the first derivative of this function. So if you want to see that, if you have the first derivative and then if you set it to 0, that means the slope at this function is going to be 0. It could be either a maximum or a minimum. So this is like an application of calculus, all right? So if I take the first derivative, it would be something like this. So minus over here, 2 times 4x to the power 3, right? And divided by 12 plus 10 over 3 and 3x to the power 2 minus 500 over 3. This becomes a constant. To identify whether it's a maximum or a minimum, we will assign this first derivative equals to 0. Okay, this is again coming from the calculus principles, all right? And then if I set it to 0, my first derivative equals to 1 over EI, and this will be the leftover when I simplify these 3 terms, right? So technically, you will see that there should be 3 possible values for x because we have a cubic function, right? There will be 3 roots for this cubic function, given that the order of the maximum order is 3. So when you calculate the values for x, I got x equals to negative 3.66 meters. Okay, so is this acceptable or not? So consider the beam. The beam is spanning from x equals to 0 and x equals to 10. But my answer is giving me a negative 3.66. That is out of the boundary that we are interested in. Therefore, this is not an acceptable answer for our beam. The second root is x equals to 13.66, which is again, that is out of our boundary because the beam is spanning out from x equals to 0 and x equals to 10. So therefore, 13.66 is also not an acceptable value. And the third root, I get x equals to 5 exactly. So this is within our boundary, and this will be where the maximum deflection is occurring, which is pretty much obvious because the loading is symmetric, geometry is symmetric, therefore the deflection should occur at the mid-span, right? So we know where the maximum deflection is occurring. Therefore, we will be able to find out what that maximum deflection is because we have the function for the deflection. So what we do is we apply or we substitute x equals to 5 to our deflection equation. This way, we will be able to get the maximum deflection of the beam, right? So I'm assigning x equals to 5, x equals to 5, and x equals to 5. So here also I got a negative number, right? Negative means downward deflection based on the sign convention that we derived in the first place. Upward deflection is positive, downward deflection is negative, all right?